Good morning, good afternoon, wherever you are in your day. Thank you as always for choosing the Maternal Chemistry part of your day. In the last video, we introduced gas properties and the ideal gas law. In this video, we're going to talk about it mathematically and then just in general mathematical terms. So, same objective, except now we're going to do the math. So just as a reminder, pressure, atmosphere, temperature, Kelvin, amount, moles, volume, liters. If you do that for everything in this chapter, you're going to be good shape. So, a word about changing condition sets before we move on and work some math, because there's really a couple versions, actually there's probably like 4 versions of PV equals nRT will work by the end of this chapter. But let's start with the 2 basic versions of PV equals nRT. One is for a single gas at a single point in time, and the other is going to be for a single gas in 2 different points in time. So what happens when we change the conditions? We heat it up, we cool it down, we add some pressure, we release some moles of gas. We add more gas inside. What happens there? So, first thing I want to do is very simple. Is the pressure the same for all gases in the universe? No. So that's a variable. So I'm going to put a 1. Is the volume the same for every gas in the universe? No. That's a variable. I'm going to put a 1. Is the amount of molecules in every single gas sample in the universe the same? No, that's a variable. Is the ideal gas constant a variable, or is that something that's the same for all of our ideal gases? That's a constant. So I'm going to just skip that over. And then, is the temperature the same for all gases? No. That's a variable or something that can change. So this is what I want you to do. Just basically take all the variables and put a 1. Then underneath it, I want you to write PV equals nRT all over again. And everything we just put a 1, we want to put a 2. So before I get into the mathematics here, let me just say one thing. The 1s are talking about time 1 initially. The 2s are talking about time 2 or a final temperature. So this is the same gas measuring the same properties these properties at the same time. This is a different time, same gas, or at least same general setup, and we can compare what happens when we change one of these to the others while keeping something constant. So the nice thing about this is you can already see mathematically, hopefully, how I've set this up. If this is equal to this and this is equal to this, we can divide both sides by the same thing. R goes away. And now we have this relationship that looks like this. And instead of, sometimes they make you memorize Boyle's law, Charles' law, Avogadro's law, the combined law. That's silliness. It doesn't matter whose name goes to which version. Get these general symbols, and then if it says we increase the volume of a flask, so we have a closed container at room temperature, and we double the volume. So it's a cylinder and we extend it out. What happens to the pressure inside? Well, if it's a sealed container, and typically these problems, they are sealed, you would assume the moles are constant. So it doesn't matter what the number is, anything divided by itself is 1. And same thing, if it's at room temperature, it's going to also be the same. So I just wanted to point out one example here where if everything cancels out, that is not 0, anything divided by itself would be 1. And then you could rearrange this, and you would say that P1 V1 equals P2 V2. So if we had the initial volume and pressure, if we change that volume, we can calculate the new pressure inside. This is actually Boyle's law. I know that because, I don't know, I read too many general chemistry textbooks. But you don't need to know that, and you get your mathematical relationship. Don't memorize these boxes. Just get this process, right? PV equals nRT. Everything that's a variable goes 1, 1, 1. Anything, then write it again underneath. Anything that changes goes 2, 2, 2, and then just divide the top by the bottom. Anything that stays the same drops out, and you have all your different relationships. So you don't have to memorize them. It's very simple, very straightforward derivation. What's that look like in a word problem? So, here's a word problem. An 8-ounce used aerosol can has only a slightly higher than atmospheric pressure inside, 1.1 atmospheres. If you go camping on a cool day, 15 degrees Celsius, and you throw the empty can into the fire, roughly 500 degrees Celsius, what's the pressure inside the can? So what's happened to the pressure inside the can? Reasonably, if you throw it in a campfire, you can imagine it increases, and then an empty can is never truly empty. There's something inside it. That's why I'm an optimist. The glass isn't half full or half empty. It's always filled with gas molecules, at least. So the cup is always full in chemistry class. It's a positive, happy place. But what I want you to do in these problems, and it's very easy in the test because the topics between enthalpy and gas laws are so different that it's easy to tell if this is a gas problem or a heat flow problem. This is clearly talking about gases. It's a pressure, if nothing else. We don't have pressures in the other chapter. I want you to go through and just underline everything that's a number. or what you're asked to calculate. And then I want you to put the symbol there. So 8 ounces, that's a volume, that's how big the can is. 1.1 atmospheres, that's a pressure, so I'm going to put a P. 15 degrees Celsius, that's a T. 500 degrees Celsius, that's a T. And they asked me to calculate the pressure, so that's a P. And if you do this, it becomes super easy. Is this a simple plug into PV equals nRT? Or is this one where you have 1s and 2s? Well, I see 2 P's, I see 2 T's. That tells me right away this is one of those ones with 1s and 2s. So let's go back to what I just had on the previous board. And talk about what's going on here. Is the pressure the same at the beginning and the end? No. Is the volume the same at the beginning and the end? Yeah, it's a sealed 8-ounce container, so that's going to cancel out. Volume goes away. Is the amount of particles trapped in that closed container the same at the beginning and end of heating? Absolutely, so that goes away. And is the temperature the same? Nope, it changes. So if I look at what's left, I'm left with a fairly straightforward mathematical relationship. Pressure 1 over pressure 2 equals temperature 1 over temperature 2. So I'm going to call 1.1 pressure 1 because that's the first one I came to. And at 1.10 atmospheres, my temperature is 15 degrees. So these have to be linked. So these are linked, and you're just going to have to read the problem to see which is talking about at the same time. A lot of times they're linked, very close to each other in the sentence structure as well. So those are linked, so they're at the same time. Now I can't use 15 degrees Celsius. I have to convert that to Kelvin. So this is going to be 15 Celsius plus 273. Gives me 288 Kelvin. Likewise, this is temperature 2. We also have to add 273 through it. So even though when you look at this, the difference between 15 and 500 degrees Celsius seems like it's, I don't know what that is, 30 times larger. It's not actually, because 15 degrees Celsius has a lot of kinetic energy. So if we're looking at the total kinetic energy of the system, you can see it's still a big difference, 288 to 773, don't get me wrong. But when we calculate this pressure, I would cross multiply. So I would get 288P equals, don't fall on it, equals 850. Divide both sides by 288. And we get our new pressure of 2.95 atmospheres. So again, might not seem like a lot of force, but again, remember an atmosphere pressure is 15 pounds per square inch. So now we're talking about a 50-pound weight on a postage stamp size of that can. And you know those cans, they're not manufactured perfectly. You put that much pressure on them and eventually the can's going to pop and burst, and then you have a very dangerous situation. So don't throw empty cans in a fireplace. But that's the general idea, and that makes sense, right? So we always do the common sense check. Temperature went up, so pressure should go up. That makes sense. They're on opposite sides. We talked about this in the last video, the relationship between pressure and temperature with Charles. This would be Charles' law if you're interested in the names. I'm not really, to be blunt. But I am concerned you can do the math correctly. So, what's one look like where it's a standard PV equals nRT? Well, I'm glad you asked that question. And I happen to have one right here ready to go. So all the ozone in the atmosphere above your head right now occupies a volume of about 325 milliliters at a temperature of 300 Kelvin and 836 millimeters of mercury. How many grams of ozone is there up there? So again, I want you to do the same thing. Find all the numbers, underline them, and then what are my units? So milliliters is volume, Kelvin is temperature, millimeters of mercury is pressure, and grams relates to amount. Not directly, but indirectly. As far as this chapter goes, that would be amount. So we can see we have a simple PV equals nRT. There's no 1s, there's no 2s, it's one condition set. So my question then becomes, and always look at R, 0.821 liter atmospheres per mole Kelvin. And that's going to tell me my units. So I'm looking for my amount. Temperature needs to be in Kelvin. Is it in Kelvin? Yep, that's awesome. I don't have to do anything. My volume needs to be in liters, and it's in milliliters, so let's convert that over. And again, don't lose track of all those skills we worked so hard to build with the railroad. Even if I do them faster in the videos, keep doing that same thing. And same thing with the pressure. Pressure needs to be atmosphere, so we need to convert that. So 836 millimeters of mercury to atmosphere. We know that relationship. 760 to 1. The This one I do need a calculator for. And that just becomes 1.10 ATM. And now we can solve for n. If we do this correctly, multiply this side, divide by those two numbers. And I get 0.0145, which is correct. Now, if you've taken enough classes with me, you know at this point I'm going to be upset because we don't have units. And I'm also going to ask you, did we answer the question? Well, if we go and look at our units, liters, atmosphere, Kelvin, we're left with moles, which is not grams. So we need to multiply, and I didn't tell you what ozone is, but ozone's O3, so we have moles of O3. Grams to moles is our formula weight. So I did want to do a problem where we had to think a little bit about our units. Convert some of them we didn't have to convert, but this general idea. Multiply by 48, and above your head right now is about this many grams of ozone. So that's what's protecting you from UV damage from the Earth. So that's a mathematical example of each of those. People usually do pretty well with them. I know they do a lot of these in high school. We'll do some in class. But let me just talk about qualitatively what's going on. And sometimes we ask these questions and students don't think they're math-based. You know, if we double the pressure, what happens to the temperature? And it's, you know, it depends on how you want to think about it. I mean, you want to think about those collisions and what's going on. You're like, oh. But if you want to make this a very, very simple math problem, I like that idea and I like that thinking. So you can do this with any relationship. If you're trying to figure out if something goes up or something goes down, just make everything 1. It's not true. I mean, it's true mathematically. If everything's 1, it's going to be 1 on one side, 1 on the other side. It's going to work mathematically. But that's just your starting place. So then if it says, what happens to a gas if you double the volume? What happens to the pressure of a gas if you double the volume while keeping the temperature the same? So you do just what it says. So if it says double the volume, that's why we start with all ones, make it easy. So double, what's twice 1? That's 2. And then ask me what happens to the pressure. So I just put P in there, and then we got all ones. So we solve for this, divide both sides by 2, and we see that the pressure is half of what we started with. Super easy, right? So let's do a hard one. What happens when you triple the temperature and cut the pressure in half? What would happen to the volume? So again, we're just going to solve for the volume. It tells me to cut the pressure in half, and I want to triple the temperature. So if I solve this expression, multiply both sides by 2, I see that the volume is 6 times larger than when we started. So again, fairly straightforward way of taking this information. Or if you just generically want to know if I increase the temperature, what happens to volume? Well, what's a number bigger than 1? I don't care. Pick any of them. Take 10, take 100, take 1. I'll do 5, just to be different. So if I simplify this, volume goes to 5. So if we increase the temperature, we increase the volume. And even more so, however much we increase the temperature by factor-wise, we increase the volume-wise by the exact same factor. So you can qualitatively do some of these questions or piston questions, or what happens if we modify one aspect of the gas with the rest of the gas. So a simple way of doing this will work with almost all your mathematical relationships. You get confused in another class, geology, physics, and you're looking just concept-wise. This will always work, this little math trick. So I hope you find that helpful. Thank you so much for your time. Have a fantabulous day.